Did everyone write down this extra homework problem?
No.
One of the nice things about writing this up in class is that you can send it off to That's a good idea. So we barely began talking about circular motion. We mentioned what angular velocity is, angular position, relation between angular velocity and period and frequency, and that type of thing. And that's what we did last time. And then at the end of class, I mentioned that if something is moving in a circle, it has to be accelerating because the velocity vector is changing. It's changing direction. So if something's moving in a circle at constant speed, let's draw a picture of this. Say you have a little mass that's moving in a circle at constant speed. And this is a radius r. This mass has to be accelerating so that its velocity vector is changing. And the magnitude of the acceleration is called centripetal acceleration. Acceleration. And it points towards the center of the circle. The acceleration does. And the magnitude of the acceleration, which I'll put a little a with a little r there, is v squared over r.
That's centripetal force?
Yeah, that's the centripetal. That is what the acceleration is of something moving at a constant speed around the circle. The acceleration points towards the center of the circle, and it has a magnitude of v squared over r. And even if it's not at a constant speed, but moving in a circle at some time with this speed, that's its acceleration. Okay? So if it's moving in a circle, acceleration v squared over r, towards the center of the circle. And we just apply Newton's second law now. And this thing has all sorts of applications. I think I'm gonna go through several applications today. 4 of them. So the first application I want to talk about is period of motion of a planet around a star or a satellite around a planet. Okay. Let's say I have a planet. I'm going to write MP for mass of the planet. And let's say that there's some satellite orbiting around here. I'm going to call this little mass M, and it's going around here in a circle. The radius R. Okay. What we're going to do is we're going to figure out how the time it takes to go around that orbit is related to the distance and the mass of the planet. So first of all, if I look at a free body diagram as I have it drawn, this little mass here, what forces are there? There's just one. Well, there's no normal gravity. There's nothing pushing on it. You just have gravity. You have the force of gravity downwards. If it's at this point. And this isn't on the surface of the Earth, so we have to use that universal law of gravity. What's the universal law of gravity? What's that force?
That was
Big G.
Big G, M1.
G,
M1.
mass of the
M2.
planet, mass
Over r squared.
over r squared. All right. Now, this is the only force that has to equal ma, right? And this force points in the direction, towards the center of the circle. And so if I'm looking at, this is ma, m times the magnitude of a in that direction. Maybe if I introduce a y direction downwards, may would be the same thing as that mar there, and it would be confusing. So this would be m v squared over r. Right. Now, this v squared is a little bit confusing because we don't really know what the velocity is, and we're trying to get what the period of motion is. But we can write v. V is related to that angular velocity. You remember that v is the angular velocity times the radius of an orbit if we're moving in a circle. So I'm going to take this v, plug it into here, and then I could write g, mass of the planet, mass of the satellite, over r squared is equal to m omega squared r squared, that's the v squared here, over r. One of these r's cancels here, and so this is just m omega squared r. Now, do you guys remember the relation between angular velocity and period of motion? So it takes omega times the period. This is radians per second times a period. That in a period it goes 2 pi radians, right? Because that means it goes all the way around. So this would be 2 pi. And so omega is 2 pi over the period of motion. Big T means period of motion. In this case. So if I take this, put it into here, I get an equation. G, mass of the planet, mass of the object over r squared is equal to mass of the satellite or object, 2 pi squared r over t squared. Now all I have to do is solve for that t. And if I go ahead and, so how am I going to do that? This is r, this is t. Okay. First thing I'll do is I'll get rid of the little m. Is that, yeah.
Why is the t squared?
Because I had an omega squared here, right?
Okay.
So I take this whole thing and square it. Good question. All right, so I get g times the mass of the planet over r squared is equal to 2 pi quantity squared times r over t squared. I can multiply both sides by a t squared, right, so I can get it up there. Up in the numerator on this side.
Where did the little m go?
I divided it out on both
okay.
sides. So this period won't depend on the mass of the satellite that's orbiting. It doesn't depend on that. This thing cancels out. I can bring this r squared over here by multiplying both sides by r squared. And make that into an r cube over there. And then these would cancel. And I could divide both sides by a g mass of the planet. getting kind of ugly.
Yeah.
So if I get t squared is equal to 2 pi squared g mass of the planet times r cubed. Now, there was a guy, Johannes Kepler, back, I think it was late 1500s, early 1600s. And he carefully looked at the data from planets orbiting the sun. And he came up with his 3 Kepler's laws of how planets orbit the sun. They are that, you know, planets move in an ellipse with the sun at one focus. That one we're not going to deal with. Another one is that the period of motion squared is proportional to the radius cubed or semi-major axis cubed. We just derived this. That one. And there's one other. Oh, equal areas and equal times. But that, we won't worry about that for now. So we just derived, this is one of Kepler's laws. Okay? And I came from just the criteria of circular motion. He does it actually with an ellipse where you use what's called a semi. Anyway, we won't worry about it. This is what this is Kepler's law for a circular. Okay. And so let's go ahead and see if we can use this really quickly. What's the period of motion of the Earth around, or of the Moon around the Earth? I think it's 29 days. 29 days. So 29 days, roughly. Equals T or Moon around Earth. Okay, and we won't do more than that. All right, I just looked this up, what the distance is. The distance between the Earth and the Moon is 238,900 miles.
Got you there. Can't see it down there.
Too low?
Yeah.
So it's R is 238,900 miles. Okay, from these two bits of information, can you get the mass of the Earth? Find mass of the Earth. Go ahead and give that a try, okay?
Can you give us big
Oh, big D. Big D?
Right?
What's big D?
6.7.
6.7 times 10 to the minus 11 Newton meter squared per kilogram squared. Okay. I'll recommend it.
Yeah, you are something to that.
Not big enough.
That's a little bit too big. Did you convert all the things to MKS units?
24, right?
Yeah.
Yeah. NP. I hate this.
We're gonna get massive financial. So I just forget it on nine. Yeah, we need to put everything in KS units. We just get one second. So 29 days, convert that to seconds. This is, that's what we can get, you know, the part of it.
1609 meters in 1 mile, right?
It'll be close.
Yeah. So to get like
You guys get 2.
that, I think my algebra is so to get the NP by itself, when I divide this whole like over
No,
there.
multiply both sides. Because you want NP in the numerator, right? Up top.
Yes.
And then divide both sides by
Okay.
What does the top, or the period need to be
In seconds?
in seconds?
All right, so how are you gonna get that? You know, it's 29 days. How many seconds are in a day?
Actually, done.
How many seconds are in an hour?
36.
3,600, right? And how many hours?
24,
How many seconds are in a day?
86,400.
Nice.
Is your calculation factor correct? Yeah.
That period, of course, isn't, you know, to that precise of a thing, so we're it's not gonna get it more than
2 sig figs correctly here, but we should get not that far off.
What was the conversion or miles to meters?
8 has to be on.
Well,
Yeah.
there's a way to do it knowing the connections between inches and centimeters, 2.54 centimeters and 1 inch.
Yes.
But we found before it's 1609, 1609. Meters is 1 mile.
Yeah, 2.1 times 10 to 28 kilograms.
We're getting close, but we still have factor 10,000 on. No, this is
Wait, for your second switch. Okay, I got this one.
I use this.
Look at the we have for blade that he's through. Can you solve that for MP?
What did you get, Brad?
So I have this MP is these two.
What you get?
It's huge, yeah. Whoa. What'd you get?
How huge your ass is.
Okay, good.
Divided by R squared. See what we get.
Is this what you did? This divided by G divided by...
2.67.
So you
I multiplied NP almost came and then T squared, NP T squared, like this. And then now he said divided by T squared.
what I did. I put in T squared,
Yes.
and I put in R cubed,
Uh-huh.
and I divided T squared by 2, and then I multiplied, and then multiplied by, and I divided by pi squared, and then I multiplied by G, and then all you have left is the inverse of that.
I know, but so that's confusing. I don't want
I just did it backwards, like I didn't solve, like I
Yeah,
solved
I
for it.
like knowing what I'm solving for, getting it on the one.
What's your go to right now?
I do 0.67.
To the 27, to the 15.
Yeah, to the 24, like I got 5.5 to 24.
It's okay.
What'd you guys get?
I don't know if I did this.
I got
My algebra. Is hard to do like rearrange it. Is there if I'm solving it?
I'm pretty sure it's
I multiplied it, canceled it out.
Which number is it? Because we have
Then
different
do I divide this
5.35
whole thing by T
It's
squared?
probably just a small difference in because it's convergent.
You're not giving me the right answer.
No, your T square is going to be multiple of G.
Multiply to what?
The G.
Okay,
What'd
who's
you
done?
get?
5.4
All right,
times 10 to the
give me
24.
some numbers here, and we'll see if it,
2.67 e to the 24.
5 point, what's that?
2.67 e to the 24.
2.67
E to the 24.
times 10 to the 24 kilograms, oh, that's close.
5.35 times 10 to the 24.
5.35 times 10 to the 24. Well, this is almost up. When you did this, did you do 4 times pi squared?
No.
2 squared 2. And that would, then those two would agree.
Yeah, I do.
Okay. Anyone else? Okay, which one?
5.4.
5.4, okay. Anyone else? Well, both of these are right order of magnitude. That means it's within a factor of 10. Good. Let's go ahead and see how to actually do this. So first of all, I'm interested in the mass of the planet. So let's go ahead and just solve for the mass of the planet. So how am I going to do that? I'm going to multiply by mass of the planet on that boxed equation and divide by t squared. So I would get mass of planet times t squared over t squared times t squared is 2 pi quantity squared. That's the same thing as 4 pi squared. Okay. Over g e r cubed times mass of planet over t squared. This cancels with this. These two t squareds cancel. And I end up with the mass of the planet is equal to 4 pi squared r cubed over g t squared. Okay? Now, we need to get what r is, and we need to get what t is. I gave it to you, but the units aren't good. This is a, because this g here is in SI units. That means every